Hi, I'm Kim Nevelstein, and I'd like to introduce IPSME, the Idempotent Publish-Subscribe message environment. How do we obtain syntactic and semantic interoperability when we assume that technical interoperability exists? Two common approaches are standardization or using a framework. The problem is that when multiple of these protocols or frameworks come into existence, then you start getting unsupported protocols and legacy systems. Syntactic and semantic mappings can be created, but these are often labor-intensive and error-prone, and there's not necessarily a single correct mapping. If protocols are updated, then mappings must also be updated. Related work is that Madni et al. In 2014 has specified 5 different interoperability cases increasing order of difficulty. The most difficult case would be systems not designed for interoperability. There's no new system development in the works towards interoperability, and systems must be interoperable with minimal redesign and modification. Noura et al. In 2019, they state interoperability as an open challenge for Internet of Things, which requires scalability and that stakeholders should not have to adapt to major changes in their system. The solution should not be dependent on their system. Selberg et al. In 2014 specified dynamic evolution with the following criteria. Systems do not need to be re-engineered as other systems are added and replaced and removed of the systems, and the complexity of the integration should not grow as systems are added to the systems of systems. So 2 techniques for gaining interoperability are usually standardization frameworks. Standardization is usually a slow and limiting solution which can stifle fast-paced innovation. It's impossible to foresee all possible usages of a standard, and a standard is possibly outdated before it can be standardized. A standard does not necessarily satisfy all stakeholders, meaning that there are missing features, and bloat. Updating a standard means that multiple versions can be in use simultaneously and risks the existence of legacy systems. For frameworks, this is similar. For a framework, we expect all users to conform to the framework. A framework must be implemented for each system or programming language that is to be supported. And updating a framework means that each system must be updated and risks the existence of legacy systems. I'd like to introduce IPSME, which is not a standard protocol or framework. It is a set of conventions that forms an architecture. Groups of participants which speak the same protocol can talk to each other. There's no need for central authority or standardization. The conventions that describe IPSME are a messaging environment, which is a pub sub with idempotent messages. Each participant of the messaging environment sends and receives in a messaging environment, and they ignore messages that are not understood. Participants can be added to the messaging environment that translates messages, and communication across messaging environment boundaries is done via reflectors. One participant in one messaging environment relays messages to a counterpart in another messaging environment. Communication between reflectors is left as unspecified. IPSME promotes interoperability by using a readily available pub-sub resource as the messaging environment. Pub-subs are usually available on most platforms, and if more than one pub-sub is used, then reflectors can be used between them. Messages must be idempotent, which promotes asynchronous communication, reduces the requirements for ACKs, and duplicate messages can be dropped. There is no specific message format specified. Participants send messages in their own protocol. Participants drop messages that they don't understand. This leads to the partitioning of the semantic and syntactic space. Mappings in IPSME are done by adding translation participants to the messaging environment. This broadens the set of participants that understand the messages, and translations can be used transitively between participants. This reduces the complexity by reducing the number of integrations required in the system of systems. The problem of schema heterogeneity is resolved by decomposing the problem. IPSME promotes scalability by using a pub/sub, which decouples the production and consumption of messages, and participants can be divided over multiple messaging environments. There is no limitation on the topological organization of the messaging environments. Reflectors are used then to redirect a message between the messaging environments. So the performance of pub/sub on a local machine is roughly the same as inter-process communication. The worst case scenario for IPSME is when we have a fully connected graph and a unate translation path between all the nodes. This means that message broadcast overhead is maximum, meaning n-1 messages are sent for the first message, and every subsequent message is another n-1 messages, leading to leading to n-1 squared messages. Message traversal is also maximum, meaning n-1 hops. Is this grim? Well, without transitivity, no communication would be possible between the systems, and overhead can be detected so that integrations can be added to the system and then reduce complexity. IPSME was tested in 3 use cases: a Minecraft Doom integration, a medical resource scheduling, and a Minecraft metaverse via MIM. For the Minecraft Doom integration, a single messaging environment was used. Minecraft Doom and a universal interface component were coupled to the messaging environment, and translation participants as well. Minecraft and Doom were re-engineered to speak with the messaging environment. They were on the same operating system and in 2 different programming languages, Java and C++. 2 translation participants were added to the system and transitively applied. Minecraft to speak to Doom via the universal interface component and 2 translations. In the medical resource scheduling use case, participants were on different platforms and different programming languages were used. There was no central authority, and this was primarily a test for fault tolerance. This was for emission failures and then redundancy. For the Minecraft metaverse via MIM, the object was tried to link every Minecraft instance in existence. 123 third-party servers were linked together. The instances were on different operating systems, Mac OS, Windows, and Linux, and they were all in the same programming language, Java. Minecraft client and server were not re-engineered. Reflectors were used between multiple messaging environments, and this formed a star topology per client that connected to the system. Minecraft proxy objects were used for client and server side. This means that the data stream between client and server was parsed, and then events were sent to the messaging environment. Also, messaging environment events could then also control the proxy objects and the data stream. In IPSME, translations are made dynamically and external to the systems being integrated. This means no re-engineering is required of the systems being integrated, and also backwards compatibility is supported. Complexity is reduced through transitivity, so the complexity of IPSME is linear. This means that IPSME supports dynamic evolution, which has 2 requirements: that systems are not re-engineered as systems are being added, replaced, or removed to the systems of systems, and that complexity of the integration does not grow as systems are added. In conclusion, to the best of our knowledge at the time of this writing, IPSME is the only interoperability solution that is independent of the systems being integrated, allows for the integration of n systems with linear complexity, and maintains scalability. IPSME supports legacy systems and is applicable to the most difficult interoperability case. Thank you.